Alright guys, let's get back to the number sense test. We're on 2018 UIL. Alright, number 36. So a regular septagon has how many sides? Well, let's remember what our shapes are. So something with 3 sides is a triangle, 4 sides is a square, 5 sides. This is where like a unique naming system comes into play. So we have pentagon, and then with hexagons we have hexagon. And later, let's skip 7 for now. We're gonna have, let's see if I can draw an octagon. We have an octagon. Octagon. And then 9 we have, I'm not going to draw that. 9 we have a nonagon? Pretty sure I have that right. Well, anyways, the point being, the front part of these answers have a certain like prefix that tells you how many sides the shape's gonna have. So pent, well that means 5. Hex, it's gonna mean 6. Oct, like octa, that's gonna be 8. Nana, that's 9. And then we got a 10, that's decagon. So that's going to be 10 sides. If I went to 11, that would be an undecagon. 12, that's a dodecagon. And I think you only really need to know like the shapes from 3 to 12 sides, pretty much. So what's 7? Well, the prefix for 7 is septagon, which is what the question's asking for. So septagon, 7 sides, so that's our answer. Septagon has 7 sides. So that's kind of like a vocab question. It's just like if you know it or you don't. And I guess you could kind of see like septa, 7, it's pretty similar. Okay, 37. So find the simple interest on $300 at a rate of 4% for 2 years. Okay, so we have simple interest on $300 at a rate of 4% for 2 years. So the way to find the simple interest on something, the formula for simple interest is equal to your principal times your rate. So principal times your rate times your time in years. So T with a subscript years to show we're talking about years. So your principal is the amount of money you're investing. Your rate is that percentage. And the years, well, that's just their time in years. So we're just going to multiply all of these together to get our simple interest. So 300 times 4%, which is like 4 over 100, times 2 years. Well, this right here, that's going to be 12 times 2, that is going to be 24. But for these kind of questions here, where you have a dollar sign, you can't just put 24. You have to put 24.00. That's crucial. You're not going to get credit if you just put 24. The graders are going to count it wrong. So you got to put 24.00. Even if there's no cents, you got to do it. Only for these dollar sign questions. Okay. So then we got number 38. So 38 looks pretty daunting, but there's a quick trick to it. And the trick is, I'll show you the two ways they ask this kind of question. But let's do the way they're doing it right now. Let's see this case. So we have this number, or this binomial on the top, and another binomial on the bottom. You know what I'll do? I'll write this like this. I'll do x minus 8 over x plus 9 plus the fraction x plus 9 over x minus 8. This is equal to sum A and sum B over C. So how can I find the B term? In this kind of question, they only ask for the B term. They'll never ask for the A or the C term. The way you find the B term, is you're going to take the difference between the numerator and denominator, or like the positive difference between them. And so that's just going to be a 9 plus an 8, right? Because we're doing 9 minus a negative 8, that's like 9 plus an 8. And that's going to be 17. And what B is going to be, B is equal to this difference squared. The answer is 17 squared, which is 289. Let me give you guys a few more examples. Okay, so let's say that I have a fraction here. Say this fraction is x plus 5 and x minus 7. What's the B going to be? Let's trace back the steps. Let's get the positive difference between the numerator and denominator of any of these. It's going to be the same. The positive difference here is 12. So B is going to be equal to 12 squared. That's 144. So now you know how to approach this kind of question when it's in this form. Binomial over binomial, plus it's reciprocal. Reciprocal meaning like you take, the top and bottom and you just flip it. But there's another way they ask this trick. Another way they might ask this trick is if, let's say, you have 7 over 5 plus 5 over 7. So we're getting rid of the binomials. Actually, let me rewrite this. Okay. So no more binomials. We have actual whole numbers. And let's say it wants us to get what our answer is as a mixed number. So how can we use this trick? Well, whenever you have two numbers like this, at least most of the time, I'll show you some cases where it doesn't work, but 99% of the time when you have a question like this, the way you get the mixed number is always going to be the same. You're going to take the denominators, so the 5 and the 7, you're going to get their product. 5 times 7 is 35. So for the fraction, for its denominator, we're going to put 35. Then, we're going to get the difference between these two numbers, so the 5 and the 7, and we're going to square it. 5 minus 7 squared, that's going to be 4. So 4 goes on top. And now what's our a going to be? Our a is always going to be, or at least 99% of the time, it's going to be 2. Just 2. Let me give you guys another example of a question like this. Let's say I had, let's say 11 over 17 plus 17 over 11. So let's remember our steps. First, let's get the product of the denominators, product of these two numbers, 17 and 11. That is going to be 187. Next, we get the difference between these two numbers. So the difference between 17 and 11, and we square that difference. So 17 minus 11 squared, that's 6 squared, that's going to be 36. And then for the a, we write a 2. This is a pretty easy trick, but I'll show you a case where it doesn't work. They usually don't ask this case, but I've seen it once before. So a case where this trick would not work would be like if I had this case. Wait, no, that would work. This wouldn't work. So let's see why this doesn't work. Let's do our steps. So let's do the 5 times the 14, that's 70. Let's do the 5 minus the 14, that's 9, or negative 9. Square it, we get 81. And then we'd put a 2. But you see we can't have an answer like this because this fraction right here is improper. So if when you do the difference and you see it's greater than our denominator, because 81 is greater than 70, well, you gotta do 81 minus 70, that's 11. We'll write that 11 here, and instead of a 2, we're gonna put a 3, like that. And why do we do that? Well, because it's like we're taking out a 1. We're taking out 70 70ths, leaves us with 11 70ths. This is just 1 and 11 70ths. We're transferring that 1. I guess we're adding that 1 to the 2 that was in front originally, turning it into a 3. So 3 and 11 70ths. So the way you know what to do is if you see that the difference of the two numbers squared is greater than the product of your two numbers. Alright, so that's 38. Let's do 39. So 5 and 1/4 is blank percent less than 70. If you recall from our first video, we had a question like this. It was percent less. Here, number 12. So some number is blank percent less than some other number. And how did we do it last time? What we did last time was we did if A technical difficulties. Okay, we said if A is blank percent less than B, and the answer was B minus A over B, right? And so in the case we had before, I think it was like 9 is what percent less than 25. We did 25 minus 9 over 25. That gave us this, which was this percent. This might not have been the exact question, but we did something like this. This is the exact same scenario, except we have two different numbers. These are actually, we're dealing with a mixed number here. But if we use our formula, it becomes a bit nasty to do. I don't like working with mixed numbers. So what can I do here to make this easier on myself? Well, let me explain what I'm about to do with an example. So let's say I were asking 2 is blank percent less than 5. The answer I get from this question would be the same if I doubled all the numbers. I said 4 is blank percent less than 10. I would get the same answer. I would get the same answer if I multiplied both numbers by the same factor, or divide them by the same factor. And we're going to use this concept to help us right now. But let me show you an example of what I mean. Maybe something a bit easier to understand. A decimal. If I said 1.25 is blank percent less than 8, this might be a bit tricky to work out, dealing with decimals. But if I were to multiply both of these numbers by 4, so I multiply them both by 4, I end up with 5 is blank percent less than 32. And now I'm dealing with whole numbers, makes it a lot easier on myself. We're going to use that same concept here. So in this question, we have 5 1/4 is blank percent less than 7. So how can I turn the 5 1/4 into a number that's nice, a whole number? I can multiply by 4, get rid of that fraction. I multiply both the 5 and the 4th and the 7 by 4. And now I'm dealing with a new question which would give me the same answer. 21 is blank percent less than 28. Now it becomes a lot easier to deal with. Now I can do my formula. I can do 28 minus 21 over 28. Right, given that this is A and B, I'm going to do B minus A over B. And this is going to give me 7 over 28, which is just a fourth, or 25%. So 25 is my answer. So remember, for that question, we kind of had to change our perspective on the question in a way that made it easier for us to solve. It's a really important skill to have in a lot of these number sense questions. Okay, so number 40 in estimation. So we have 376 times 49 squared divided by 51 times 124. So again, this is something I see a lot for the estimations. Round, make it easier on yourself. And I'll show you what I'll do right here. I'll change this 376 into a 375. I'll change this 49 into a 50. I'm going to change this 51 into a 50. And I'll change this 124 into a 125. Now look at what I've done. I've made it a lot easier myself, and here's why. So this term right here is the same thing as 375 times 50 times 375 times 50. Because I'm squaring it. I'm multiplying it by itself twice. And I'm dividing this, now symbolizing by this fraction bar. I'm dividing this product by 50 times 125. And look what happens. One of these 50s from the denominator cancels out with a 50 from the numerator. And then this 125 divides perfectly into this 375, leaving me with a 3 on the top. And so that's why I rounded here, so I can get these clean cancellations. And so now I've got some clean numbers to work with. All I have left in this question is 375 times 3 times 50. So what can I do here? Well, I can multiply the 50 and the 375. Remember, multiplying by 50, oh, let me erase some of this work so I have some extra space. I'm going to do the 375 times the 50 first, and then I'll multiply by the 3 later. And remember, multiplying by 50 is the same as multiplying by 100 and dividing by 2. Same thing. So what I'll do is I'll divide this 375 by 2, and then shift the decimal place twice to the right. But I'm going to round a little bit to make it easier myself, so I'll round again here. I'm going to round this 375. I'll round it to a 380. So I'm going to divide by 2 and then multiply by 100. That's going to get me 19,000. And now I multiply by the 3, and I'll get 57,000. Now hold up. One more thing I think is very important for estimations is to know just how much you're rounding. So if you know you're rounding up a lot, that's getting you very close to the upper limit of that estimation range that you're allowed to answer in. So, because I rounded up a lot here, right? I rounded that 375 to a 380. What I'll do is I'll take what answer I got, so this 57,000, and I'll subtract a good amount to kind of adjust for that. So I think a good amount is about 3,000. Because I feel that this answer puts me in a safer range than my original answer, this 57,000. So I'll go with 54,000. And so again, when you're rounding, keep in mind how much you're rounding. If you think you're rounding down too much, maybe add a few. Like, in this case, if you got like 50,000, you think that's too low, maybe add a few thousand. If you got an answer like 60,000, you think you rounded up too much, maybe subtract a few thousand to account for that rounding. So I'll go with 54,000. If I check my answer key, I see that the range for this question is 50,992 to 56,359. So if I went with my 57,000, I would have been just barely out of the range. And again, for these estimation questions, you can approach them any way you want, because there's no correct method to solve any estimation question. You gotta get creative and go with your own approach. Whatever is going to be the fastest and makes the most sense to you. So solving estimation questions does take a lot of time. And I do feel like usually when a person misses a question on a number sense test, it's usually an estimation. Okay, so that's number 40. Number 41, sum of the prime divisors of 30. We gotta do prime factorization. Let's get the prime factorization of 30. I could split it up into a 5 and a 6. 5 is prime, so I'll circle it. That side of the tree, this little factor tree, is finished. 6 splits up into 2 and 3, which are both prime, and so we're done. The prime factorization of 30 is therefore 2 to the first times 3 to the first times 5 to the first. Of course, you wouldn't be drawing out this factor tree on the math test. You would just be thinking about it in your head, splitting up those factors. And we see that 30 is 2 times 3 times 5. So there are 3 prime factors, 2, 3, and 5. Now we want the sum of the prime factors, or prime divisors. So that's going to be 2 plus 3 plus 5. It's going to be 10. So number 42. So find x if 4 to the x equals 32. So this takes a bit of algebra knowledge, so let's break this question down. 4 to the x is equal to 32. Well, I know what 4 is. 4 is 2 to the second. And 32 is 2 to the fifth. It's a power of 2. And when I have, so this is my equation. So when I have this exponent, so this little 2 right here, so I have a number raised to an exponent, which is then all raised to another exponent, so this x, then my answer here is going to be 2 to the 2x. It's like what you're doing here is you're multiplying. We're saying this is equal to 2 to the fifth. And so really what this question has now become is 2x equals 5. Because these have the same base, we're only going to look at those exponents to make sure that they're equal. So we're going to divide by 2 on both sides. This cancels out. We're left with x equals 2.5. Another way you could have approached this question is that you could have seen, or you could have thought to yourself, okay, I know what 4 to the first is, that's 4. I know what 4 squared is, that's 16. I know what 4 to the third is, that's 64. So it can't be a whole number. It's got to be between 2 and 3. I know that 4 to the 1/2 power, which is the same thing as the square root of 4, well, that's 2. I know I'm looking for what x in 4 to the x gives me 32. And I see that 32 is double 16, so it's like I have this 4 squared, out of this 4 squared term, times a 2, which is really a 4 squared times a 4 to the 1/2 power, which that's the same as 4 to the power of 2 plus a half, which is 4 to the 2.5. And that's my x. Okay, 43. This many feet is how many miles? So I guess this is a conversion you guys got to memorize. 1 mile is equal to 5,280 feet. 5,280 feet. Which is also equal to 1760 yards. 1760 yards. And so, to see how many miles is this many feet, I'll just do this many feet times 1 mile per 5,280 feet. So units of feet cancel out. So I'm really doing 5,280 divided, 1320 divided by 5,280. And that gives me just 1/4. So the answer is 1/4 of a mile. Okay, so 44. This is a simple algebra equation. So if this equation's true, then what's k? So let's square both sides. The square root and the square cancel out. I'm left with 4k equals 36. Now I can divide by 4 on both sides. These 4's cancel out, and I'm left with k equals the quotient of 36 divided by 4. That's 9. So k is 9. $45. So this is also a really important trick to know. So I want to find the difference of these two squares. So whenever you have a squared minus b squared, a and b being some, two distinct integers, the answer is always a plus b times a minus b. Always. So we can use this trick to our benefit here. Instead of evaluating 35 squared and 40 squared, I can instead do, while substituting this, I can instead do 35 plus 40 times 35 minus 40. And that's going to be 75 times a negative 5. And that's just going to be a negative 375. And that's my answer. Let's do another example question with difference of squares, because this is a very important trick to know. So let's say I wanted to find the difference between 19 squared and 11 squared. So what I could do is I can do 30, their sum, times 8, their difference. And that is going to be 240. So now you know how to solve any question where it's asking for the difference of two squares. Okay, 46. 46, I want to make sure you guys get this one. So 5 to the power of 6 divided by 7 has a remainder of blank. So how can I do this question? There's a simple trick. Immediately, I can put the answer as 1. How did I know that immediately? It's because of something here called Fermat's little theorem. I believe it's Fermat's little theorem. Now, what does Fermat's little theorem state? It states that whenever you have any n, any integer n, raised to the power, or any natural number n raised to the power of p minus 1, divided by p, that the remainder is always equal to 1. And so what does that mean in practice? Well, if I had some number, let's say 13 raised to the power of 16 divided by 17, keep in mind, look at this. This number we're dividing by, that's a prime number p. We just call it p to show it's a prime number, p for prime. And this exponent right here is 1 less than p. It's 16. 17 minus 1. And we have this number 13. Just any natural number. If these conditions are satisfied, this should be 1, a remainder of 1. So a remainder of 1. Now this here is the simplest version of this kind of question you'll see asked. Another question they could ask, what if we add 5 to the 7th power divided by 7? So instead of having this natural number raised to the p minus 1 power, it's raised to the p power. So what can we do? So let's think about this. This is the same, this number right here, let me erase this, give me some space. I have 5 to the 6, if I have this, 5 to the 6 times 5 to the 1st, that's the same thing as 5 to the 7th. And I'm dividing this by 7, and I'm looking for that remainder. I already know that if I look for the remainder right here, then I'll get 1. Right? So let me show you what I mean. So in terms of remainders, this is going to have a remainder of 1 by Fermat's little theorem. That's what it tells us. But I still have that extra 5 hanging around, so what do I do with it? Well, to get the new remainder of 5 to the 7th, instead of 5 to the 6th, I'm just going to multiply by 5 to the 1st. And that is going to give me 5. So 5's my answer. This would have a remainder of 5. Let's take it another step further. What if it asked 5 to the 8th? Well, then this exponent here, we're going to do like the same idea here. I know that 5 to the 6th divided by 7 has a remainder of 1. And so I'm going to multiply that remainder of 1 by 5 squared, those extra 2 5's I still have lying around. And that's going to give me 25. But I can't have a remainder of 25 when I divide by 7. 25 is greater than 7. So the way I'll get the remainder now is I'll just do 25 divided by 7 and see what that remainder is. So 25 divided by 7, that gives me a remainder of 4. And so 5 to the 8th divided by 7 gives me 4. I want to make sure you guys understand this because this is one of the tougher number sense concepts to get a grasp of. I'm going to take it one more step further. what if I asked for, I'm going to do one more question after this actually. So what if I asked for this right here, 5 to the 12th. 5 to the 12th, that's 5 to the 6th squared, right? Because that's just 5 to the 6th times 2, it's 5 to the 12th. And I already know that 5 to the 6th is going to have a remainder of 1. So the way I'd get what the remainder is for 5 to the 12th, I just get that remainder of 1 and I square it, still gives me 1. One more step further. It's the last one I'll do. 5 to the 13th power would be this 5 to the 6th power squared times a 5 to the 1st power. And that would be a remainder of 1 squared times 5, which would just give me a remainder of 5. And so this remainder here would give me 5. So those are like all the questions they could ask about Fermat's little theorem. You ever see this number raised to a big exponent like 6 or 5 or anything above that, divided by some prime number? You want to know what that remainder is? Now you know what to do. Use Fermat's little theorem. Okay, 47. So if x to the 2x plus 2y equals 16, then what is x plus y squared? So let's solve for x plus y. Just looking at this, I know that this has to be 4, because 2 to the 4th is 16. So that means 4 is equal to 2x plus 2y. If I divide both sides by 2, I'll get that 2 is equal to x plus y. I can substitute in this value for x plus y. So x plus y squared equals 2 squared, which is equal to 4. And that's my answer. It's another quick algebra question. Okay, so number 48, the sum of the reciprocals of all the positive integral divisors of 20 is. That sounds like a nasty question. That'd be adding 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 5 plus 1 over 10 plus 1 over 20. I can't do that much fraction adding. It takes too much brain power. There's got to be an easier way, and there is. But first, I need to show you how to do another type of question. This also involves prime factorization. Let's get the prime factorization of 20. That's 2 squared times 5. 2 squared times 5 to the first. So the type of question I'm going to show you right now is how to get the sum of all the positive integral divisors of 20. Not yet the sums of the reciprocals of them. Let's just find out how to find the sum of all the regular divisors of 20. How can I do that? I gotta use what I get from my prime factorization. So to get the sum of, really this is the sum of the factors of 20. So the sum of factors, the way you can get that, you're going to look at each of these numbers here. So what do we've got? We've got 2 squared. And what I want you to do is you're going to add all the powers of 2 going down from whatever you had here to 2 to the 0th power. So I have 2 squared, so let me go down. I'm going to add the 2 squared, I'm going to add 2 to the 1st, and then 2 to the 0th power. That's going to be 4 plus 2 plus 1. This is 7. And you're going to do the same thing for 5. You're going to add all the powers of 5 going down to 0. So I have 5 to the 1st plus 5 to the 0. So 5 to the 1st plus 5 to the 0. That's 5 plus 1. That's 6. Now I'm going to take these sums that I got for each prime number that I have in my prime factorization. Now multiply them. And that product gives me the sum of the factors of 20. Let me prove it to you. The factors of 20 are 1, 2, 4, 5, 10, 20. 1 plus 2 plus 4 is 7, plus 5 is 12, plus 10 is 22, plus 20 is 42. Let's do another example to get us familiar with this. Let's say I had 60. So now, what I've got, my prime factorization is 2 squared times 3 to the 1st times 5 to the 1st. So I'm going to add all of these factors. For each prime factor, I'm going to add all of their powers going down to 0. So I have 2 to the 2nd, I'm going to add 2 to the 1st, and then 2 to the 0th power. That's 4 plus 2 plus 1, that's 7. Let's do it for 3. I have 3 to the 1st, I'm going to add 3 to the 0th power. It's going to be 3 plus 1, that's 4. Lastly, I do that with the 5 to the 1st. So I have 5 to the 1st power. I'm going to add that 5 to the 0th power. So that's going to be 5 plus 1, and that's 6. And now I just multiply all these numbers. And this product here, I believe, gets me 168. Let me just verify. Yeah, 168. And again, I'll prove it to you right now. So the factors of 60 are 1, 2, 3, 4, 5, 6, then 10, 12, 15, 20, 30, and 60. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21, plus 10 is 31, plus 12 plus 12 is 43, plus 15, 58, plus 20, 78, plus 30 is 108, plus 60 is 168. So it holds true. And so now you guys know how to get the sums of the factors of any number using prime factorization in this trick where you take each prime factor and add all of their powers going down to 0 and get the product of that sum, all those sums. And now let us return to our original question on 48, which was the sum of the reciprocals of all the positive integral divisors of 20 is. And so how can I get the sums of the reciprocals of the factors? So to get the sum of the reciprocals of all the factors, I'll get my answer. So let's do it with 20. It's 2 squared times 5 to the first. So 4 plus 2 plus 1 is 7, and 5 plus 1 is 6. Multiply it, I get 42. That's how kind of you want to do it, just real quick like that. So 42. And the way I get my answer is I'm going to take this number, the sum of all the factors, and I'll just divide it by the number itself, by 20. And that answer gets me 2.1. That's my answer. So, going back to what we got for 60, for example, we knew that the sums of the factors was 160. And so the sums of the reciprocals of the factor would be, all the factors would be 168 over 60, which would be 42 over 15, which would be 21 over 5, which would be, whoa, I messed up somewhere in there. Divide both by 5, no, by 3. My bad. Yeah, that gets me 2.8. Alright, moving on. Okay, 49. Find the 6th hexagonal number. You might be saying, what's a hexagonal number? I'll show you. First, let's talk about some other numbers. So this is a very important one to know. So the triangular numbers, using this little pound sign to represent number here. So triangular numbers. So what a triangular number tells you, let's say I had a point. Right? Let's say I made a triangle like this, right? I could say that the number of points I have to make this triangle is the second triangular number. I'll show you what I mean by that. Then this triangle right here, that's the third triangular number. And this number right here, number of dots I use to make this triangle, that's the fourth triangular number. So this is the first using, if it has 1 row, it's the first. 2 rows, it's the second. 3 rows, it's the third. 4 rows, it's the fourth. And really, the pattern goes like this. 1, 3, 6, 10. Conveniently, the triangular numbers also tell you what the sums of consecutive numbers are. The second triangular number tells me what 1 plus 2 is. That would be 3. The third triangular number tells me what 1 plus 2 plus 3 is. It's 6, right? And the reason it tells me that is because these rows are increasing by 1 each time. So I have 1 dot in the first row, then 2 dots in the second row, and 3 dots in the third row. The fourth one tells me what 1 plus 2 plus 3 plus 4 is. So that's 10. So triangular numbers, you'll see them all the time. All the time. Usually when we use them, when we use triangular numbers, we use them to find out the sum of a long sequence of consecutive natural numbers. Like, what's the sum of all of these numbers up to 21? What I'd do is I'd find the 21st triangular number. But how do I find a triangular number? Do I just envision a triangle with 21 rows and count all the points? No, that takes too long. That's weird. Wouldn't want to do that. There's a formula. The formula to find any triangular number, the nth triangular number, is n plus 1, or n times n plus 1, divided by 2. So, let's test it out. The first triangular number is 1, so that has to be 1 times 2 over 2, which is 1. The second triangular number is 3, so it has to be 2 times 3 over 2, checks out. The third triangular number is 6, so let's plug in 3 for n. This checks out. The fourth triangular number is 10, so that has to be 4 times 5 over 2, and it checks out. And so back to that small question I asked earlier, what if I wanted the sum of the numbers 1, 2, 3, 4 all the way to 21? I'd find the 21st triangular number. So I'd plug in 21 into the formula. So 21 times 22 over 2, that's going to be 21 times 11, that's going to be 231. After triangular numbers, we have square numbers. And the formula is just, well, n squared. You already know that. And what a square number represents is like, if I have a 2 by 2 square, that's the second square number. If I have a 3 by 3 square, how many dots do I have to use? That's the third square number. A 4 by 4 square, the number of dots I use here is equal to the fourth square number, and so on. Moving on, we have the pentagonal numbers. The formula here is n times 3n minus 1 over 2. And again, it means forming this pentagon. And how many dots do I need to form this pentagon? And then this pentagon. It's like something like that, right? And that's the formula. And then hexagonal. The formula is going to be n times 4n minus 2 over 2. I'm going to rewrite the square one. See if you guys see a pattern in these formulas. So do you see the pattern? pattern here is that this n coefficient, which, in this first case, is technically 1, right? These coefficients are always increasing. Triangular, square, pentagonal, hexagonal, always increasing by 1. And then this number you're adding on to it, in this term, it's always decreasing. Positive 1, 0, negative 1, negative 2. And so we could probably predict that the next formula in this case for the septagonal number would be n times 5n minus 3 over 2, just based on that pattern. But really, the question, the questions here that they ask usually are limited to just triangular to hexagonal. That's triangular, square, pentagonal, hexagonal. I think I once saw them ask for octagonal. And the way you get that formula, you look at this pattern, it would be n times 6n minus 4 over 2. And so knowing these formulas, you can find any triangular number, any square number, any pentagonal number, any hexagonal number. And so, going back to what the question originally asked for, we know what the formula for hexagonal numbers is now. And I want to find the sixth hexagonal number, right? And so I'll just substitute in 6 for n. So 6 times 4 times 6 minus 2 over 2. That's going to be 6 times 22 over 2, which is 66. So 66 is my answer for 49. Though, this hexagonal number formula, you can memorize it another way. The way I usually do hexagonal numbers is because I can cancel out like a factor of 2 here, and this just becomes 2n squared minus n. I plug in 6, I get the same answer. So you could memorize either n times 4n minus 2 over 2, or 2n squared minus n. Both give you the same answer. Both are the representations for hexagonal numbers. Personally, I think 2n squared minus n is faster, but whatever works for you. Okay, number 50. So here's a trick to estimate the square root of any number. I'll show you guys. So let me make an example question first. Let's try 14,519. And I want to get an estimate of this number. So how can I get an estimate? The trick, let's cancel out the last 2 digits. Just ignore them. I guess not cancel out, it's not the right word. Ignore them for now. Let's think about the square root of 145. Let's think. What is 145? What square numbers is 145 near? If you've got your squares memorized, you know that's between 12 squared and 13 squared. Those being 144 and 169. Now, which one is it closer to? Let's think about that. I would say it's closer to, 12 squared. So this number right here is about 12. Now, if I went another step further and tried to kind of estimate what the next digit would be, I think just how close is it to 12? Well, because this one's really close, I'd probably say it's like 12.0. Okay, so now what do I do? How do I solve the original question of 14,519, getting the square root of that? Well, when I cancel out those two digits, it's like I removed a factor of 10. So I've got to put it back. So the way I do that is I'll just shift this decimal place to the right once, symbolizing multiplying by 10, and get that the square root is approximately 120. And if I look here, this calculator, I'm getting the square root of this number. It's pretty darn close. It's pretty close. So let's apply this trick one more time to another example. Then we'll do it with this question. Okay, so let's try 149. Or no, 14,955. I'm estimating the square root. So let's ignore these last two digits for now. Let's only look at the square root of 149. What's that close to? Well, again, it's between 12 squared and 13 squared, which are 144 and 169. It's closer to the 12. I'd say this is about 12. If I go one step further and try to estimate what that digit beyond the decimal point is, I think just how close is it to 144? It's not as close as the last example, like 145. So instead of saying 100 or 12.0, I'd probably put it a little farther. I would say probably 12.1. Now, to solve the original question of the square root of 14,955, I've got to add back that factor of 10 that I pulled out. So I shift the decimal place once to the right, and I end up 121 as my answer. And I look at my calculator and I see it's a little off, but it was closer of an answer than if I were to just put 120. So I always try to estimate to that third digit. Okay, so let's apply this to number 50. So let's do our trick. Let's ignore those last two digits. Let's only look at the square root of 120. And that's between 10 squared and 11 squared, which is 100 and 121. Now, which number is it closer to? It's closer to 11 squared. Now before I write 11, I gotta think. It's gonna be less, it's slightly less than 11 squared. So should I put like 10.9 or 10.8 instead? Well, because it's really, really close, only one away from 11 squared, I'm not gonna bother with that third decimal point. I'd probably guess it's like 11.0 and then something. So I'll say it's about 11. Now I gotta return that factor of 10 I pulled out. I shift the decimal one place to the right, and I get 110 as my answer. And the range for this question is 105 to 115, so we were right in the middle. So this was a very accurate answer. Now let me show you guys a few other ways they can ask this question. Let's say they asked the same question, only difference being it was 1,201,800. It's huge. How can I estimate that? Let's do our same trick. But instead of, well, let's cross out these last two digits. I can't really estimate the square root of 12,018. It's a little too big. Let's cancel out another two digits. And then we do the square root of 120 to estimate that. And that's about 11. The step that we change now is that because I canceled out two pairs of digits, that means I have two pairs or two factors of 10 that I pulled out. So I've got to return it by, instead of shifting the decimal place once, I've got to shift it twice to return those factors. And my estimate is about 1,100. And if I look at my calculator, and I'm estimating this square root, that's also pretty close. So with bigger numbers, just cancel out more pairs of digits. And I'll let you guys try this one on your own. If I have a cubic, I'm estimating a cube root of a number. Like, let's say, this. What do you think I would do here? Ignore 3 digits at a time. I'd estimate this cube root, which is like 7. And then I've got to shift the decimal place once to the right, because I cancel out one group of 3 digits. This is about 70. And I look at my calculator. Alright, I get the cube root. Very close. So now you know how to estimate square roots, cube roots. Heck, if they asked for the 4th root, we'd ignore 4 digits at a time and think what powers of 4 is that number between. Estimate, shift the decimal place, put it as our answer. So now you guys know. Because they've asked about cube roots before. They will ask. Okay, let's shift it down a bit. Almost done with the 3rd column. Okay. 51's asking for the vertex of a parabola with this equation. Okay. So how can I find the vertex h comma k? So I need to find the vertex so I can add that x and y coordinate together, which is what it's asking for. So the way I find the x coordinate in my vertex, there's a shortcut. The shortcut is to find h, it's equal to negative b over 2a. That's very similar to the sum of the roots, which, if you guys remember, that shortcut was negative b over a. It's like we're dividing it by 2. Why is that the case? Well, take a look. Let's say this is not the equation of the graph, I'm just graphing a random graph. This is a parabola. And if these are the roots, right, let's say like they're at 1 and 3. And I want to know what the x-coordinate of my vertex is, which should be directly between the two roots. It should be the average of the sum of the roots. It would be the two roots added divided by 2. And because the sum of the roots is negative b over a, I divide it by 2, I get the average. I get the x-coordinate of my vertex. So that's why negative b over 2a gets you your x-coordinate of your vertex. So let's try it out. Let's see what we get. So my b is negative 4. My c is negative 5. My a is 2. So negative 4 over 2a. So that's going to be 4 over 4. That's 1. And now, to get my k, I just plug in what I got for my x-coordinate into the equation to get my y-coordinate. So 2 times 1 minus 4 times 1 minus 5. Well, that's going to be 2 minus 4 is negative 2 minus 5. That's going to be negative 7. So my h and my k is equal to 1 comma negative 7. I add my coordinates, I get negative 6. So there's a little algebra question for you guys. And another trick to learn the x-coordinate of your vertex. Okay, 52. I have 3 minus I squared plus 6i. How do I do this? Well, let me expand this right side. Well, wait, how do I expand it? And what is I? You might be asking yourself. I is a special number. I is equal to the square root of negative 1. But you can't get the square root of a negative number. At least not normally. I is what we call an imaginary number, hence the letter I, right? And they're useful in a lot of applications of mathematics. They're well beyond number sense. The thing to know, though, is I is equal to the square root of negative 1. If I did I squared, that would be negative 1. If I did I to the third, that would be negative I, because it would be negative 1 times I. If I did I to the fourth, it would be 1, and I to the fifth, it loops around again. It's the same as I, because it would be like 1 times I. So I is the square root of negative 1. I'm going to just put it here in case you guys forget. It's big box. I is equal to the square root of -1. Okay, so let's expand this. Remember, when we expand a number, we have, okay, well, a minus b squared, that's going to always be a squared minus 2ab plus b squared for any two numbers a and b. And if I had a plus b squared, that'd be a squared plus 2ab plus b squared. Always. We're doing 3 minus I, so we're going to be using this one. Okay, so a squared, that's 9. So minus 2ab, so minus 2 times 3 times negative I, it's going to be plus 6i, or negative 2 times an I times, wait, did I do that right? That's minus 2 times 3 times negative I. Oh, yeah, nah, that should be I. Yeah, so this should be minus 6i. My bad, guys. And then I squared, well, we said earlier, I squared is -1. So, minus 1. This is my a squared, my minus 2ab, and my b squared. So I'm taking this and I'm adding 6i. Well, these terms are going to cancel out, right? This positive 6i and this negative 6i. So I'm just left with 9 minus 1, which is 8. Alright. 53. So we're multiplying these two numbers in base 6. We have 135 base 6. Remember, that little subscript 6 symbolizes you're dealing with base 6. And then 4 base 6. And I want my answer also in base 6. Now, how would I multiply two numbers in different bases and get a number in the same base? Would I need to convert each of these numbers here to base 10, work it out, and then convert back to base 6? No. There's a much easier way. You're just going to multiply like you normally would with one extra thing you got to do. So I'll show you what I mean. So to get this answer in base 6, I'm going to multiply the 5 and the 4. Let's think about what I get. I get 20. But before I write down the 0 and carry the 2, like I would if I'm normally multiplying, let's think. What's 20 divided by 6? Do 20 divided by 6. What do you get? You get 3 with a remainder of 2. So once you get that, you're going to actually write down your remainder when you get the product of 5 and 4 and divided by 6, your base. So again, to recap, we did 5 times 4, which was 20. We divided it by our base, which was 6. We got 3 with a remainder of 2. And so we write down our remainder, and we're carrying 3 now. We're carrying 3. So let's keep these 3 fingers. Okay. We continue now. Now we're doing 3 times 4. That's 12. Let's add on those 3 that we're carrying. That's 15. Now do 15 divided by 6. What do you get? You get 2 with a remainder of 3. So we're going to write down the 3, write down our remainder, carry 2, carry our quotients. So we're carrying 2. And now we do our last step. Let's do 1 times 4. That's 4. I'm carrying 2, I gotta add those 2 back. So 4 plus 2, that's 6. Divided by 6, what do I get? I get 1 with a remainder of 0. So I gotta write down the 0, carry the 1. And because there's no other numbers to multiply, I'll just write that 1 that I have, that I've been carrying. I write it down. That's my answer. 1,320. Now that process might have been a little complicated. Let's do 2 practice problems to get it engraved in our heads, get us more familiar with this type of multiplication. So let's say I have 123 base 7 times 4. What would I get as my answer in base 7? So let's multiply it out. Base 7. Let's do the 3 times the 4. That's 12. Divided by 7. That's 1 with a remainder of 5. So let's write down the 5. Carry that quotient, so we're carrying 1. Now let's do the 2 times the 4. That's 8 plus the 1 we carried. That's 9. Divided by 7, that's 1 with a remainder of 2. Let's write down the 2, carry our quotient of 1. Lastly, let's do the 1 times the 4. That's 4, carrying 1. We gotta add it back, so 4 plus 1, it's 5. And we're done. Let's do one more example. One more. Let's try 287 base 9 times 2. I want this answer in base 9. So let's do the 7 times the 2, that's 14, divide by 9. I get 1 with a remainder of 5, so I write down the 5, carrying that quotient of 1. We're carrying that quotient of 1. Let's do the 8 times the 2. That's going to be 16 plus the 1 I carried, 17. Right? Now let's divide by 9. So 17 divided by 9 is 1 with a remainder of 8. So I write down the 8, carry that quotient of 1. Lastly, let's do 2 times the 2. That's 4 plus the 1 I'm carrying. That's 5. So I write down the 5. This is my answer in base 9. So I hope now you're more familiar with multiplying bases. It's a little like regular multiplication, just a bit different. Okay, 54. So I have log base 3 of 9 and log base 3 of 27. And I want to add these. So this is a pretty easy question, but you gotta be familiar with logarithms. in case you're not familiar, what a logarithm says, so let's say I had log base, this is my base. The way you'd say it is log base A of B. So if I have log base A of B, what that's saying is, I have x equals log base A of B. That's saying that A to the x power equals B. So really what it's saying is A to what power gives me B, right? And so here, this question, or in this part of the question, where it's asking for log base 3 of 9, that's saying 3 to what power gives me 9? 2. It's got to be 2. 3 to the second power equals 9. So log base 3 of 9, well, that's just 2. Let's look at the second part. We're adding on log base 3 of 27. So what that's saying is 3 to what power gives me 27? That's 3, right? And so that part of the answer is 3. And so I'm going to add these two answers I got together, and I get 5. That's my answer for this question. So now you're more familiar with logarithms. I'll give you like one little question. If I had log base 7, 49, what is that? 7 to what power gives me 49? That's 2. And if I had log let's say log base 16 of 4, that would be 1/2, because 16 to the 1/2 power, or the square root of 16, that gives me 4. Alright, so number 55, 2 dice are rolled. What are the odds that a 4 was rolled? So this, okay, you gotta memorize this. So I have 2 dice. Right? 2 dice. The dice, you know, they're labeled 1, 2, 3, 4, 5, 6, right? So I'm going to roll these dice. I'm going to get the sum of the numbers that land on top. So these top numbers. Let's think of the possibilities I have here. Can I get a sum of 1? No, because the smallest number on each dice is 1. The smallest possible sum I can have is 2. It's the largest possible sum I can get. That's 12. I have 2 6s on the top. And then I have all the other numbers in between. So let me write it like this. And so something to memorize is how likely each of these are to occur. So a 2 has only a 1 out of 36 probability I'll come back to that later. Keep this in mind. We're talking about probabilities here. Probability. A 2 has a 1 out of 36 probability of showing up. A 3 has a 2 out of 36 probability. A 4 has a 3 out of 36 probability. A 5, a 4 out of 36. 6, a 5 out of 36. And then the most likely outcome when you roll 2 dice is a 7. It's the most likely outcome. And then it starts going back down. An 8 is a 5 out of 36. A 9 has a 4 out of 36. 10, 3 out of 36. 11, 2 out of 36. And 12, a 1 out of 36. And all of these probabilities added together sum to 1, right? So these are all the total possible probabilities I can have. And so you kind of just have to memorize it. That 2 is 1, 3 is... No, 2 is 1 out of 36, 3 is 2 out of 36, and it increases all the way up to 7, which has a 6 out of 36 probability. And then it goes down. 7 has a 5 out of 36, 9 has a 4 out of 36, all the way down to 12, which has a 1 out of 36. And this is actually not too bad. But you may want to just put in some time to memorize these. Okay. Now, also, I'm pretty sure it's asking like odds that a sum of 4 was rolling. And so, if I look at the probability, I see it's 3 out of 36. But it wants the odds. So what are the odds? What is the difference between odds and probability? The difference is that probability is what you want over the total, whereas odds are what you want over what you don't want. And so usually what that means is odds are what you want over the total minus what you want. The total minus what you want being what you don't want. And so using that definition, if there are 3 ways out of 36 in which it satisfies this condition, and 36 is the total, then the number of outcomes that I don't want is 36 minus 3. It's 33. 3 over 33, it's going to be 1 over 11. And that's the answer for 55. So now you know the difference between odds and probability. Probability is what you want over the total, whereas odds is what you want over what you don't want. Make sure you memorize this little list of the dice probabilities as well. Rolling 2 dice. Alright, number 56. In Pettville, 35 families have cats, so 35 have cats. 24 have dogs. And 12 have both. Wow. Okay. How many families are there? So to solve this question, typically we use a Venn diagram to kind of think about what the question's talking about here. Say this circle represents cat owners and this circle represents dog owners. Okay, so in this intersection here would be the amount they both share. We already know what that is. In this intersection, there are 12 people, 12 families, at both. But I can't put 35 in here because then the total amount would be, the total amount of cat owners would be 35 plus 20, which isn't true. This is actually 23. The total amount of cat owners minus the amount of cat and dog owners. This little section right here, this little crest, this area right here represents the owners that have only cats, not cats and dogs. So that means 23 have only cats, 12 have both cats and dogs. So that means in total, 35 have cats. And so using that logic, how many dog owners are in this crest? There are 24 total dog owners. That's equal to the amount of, people who have both cats and dogs, and the amount that have only dogs. And so that number, the amount that has only dogs, has to be 12. 24 minus 12. And now what I'll do is I'll add up each of the sections here in the Venn diagram. So 23 plus 12 plus 12. That gets me 47. That's how many total families there are. That's like the way with Venn diagrams, but there's a much quicker way. The quicker way is just to take the total amount of owners we have. So we have 35 cat owners and 24 dog owners, right? So we're going to add up the families that have cats, the families that have dogs, and subtract the amount that have both. And that's also going to get us 47. Our answer right there. That's a lot easier. That's really easy. But why does it work? Well, let's look back here. To get our answer, we had to add up each of these sections here in this Venn diagram. So, let me symbolize it with this color. We have the cat owners here in this section, plus the dog owners in this section, plus the amount that have both. The total amount of cat owners represents the green section and the blue section, right? Because 35 represents, both of these circles right here. Both of these sections, I mean. And the dog owners, that represents the orange section and the blue section, right? Both of these sections here. And lastly, the section that represents both, just this section here, blue. And remember, what we want, the total number of families, that's equal to the green plus the orange plus the blue. The amount that has only cats, the amount that has only dogs, and the amount that has both. We want the sum of these. And if I take these sections, add them together, I get 1 green, 1 orange, and 2 blue. But what I want is 1 green, 1 orange, and 1 blue. So that section where I have both cats and dogs, that's overrepresented. So I gotta subtract the amount that have both. That's why I subtract this extra section, leaving me with the sum of the families that have only cats, only dogs, and both cats and dogs. So that's, I guess, the long explanation in case you wanted it. But, again, the quick way is to get the sum of A and B, and the sum that have both A and B. Get the sum of A and B and subtract the ones that have both. So let's say that, I don't know, we get a survey of some kids at a high school, and 21 have a PS4, and 19 have an Xbox, and 7 have both. Then how many kids did we survey? Well, it'd be 21 plus 19 minus 7. 33. There's an example. So our answer here was 35 plus 24, which is 59, minus 12, 47. Alright, next, number 57. So we have what we call an infinite geometric series. So that's when I'm adding a half, a fourth, an eighth, a 16th, and so on. So let's break it down. Infinite geometric series. What does that mean? Infinite, meaning it goes on forever. So we're adding infinitely many terms. Series, meaning like we have multiple terms we're adding together in series. And geometric, meaning that each term, like each next term in the series, we're multiplying by some constant r. Multiplying by some constant r to get the next term. In this case, r is pretty easy to figure out. R is just 1/2. So that's what an infinite geometric series is, but how can we get the sum of one? The formula is equal, the sum is equal to our starting term, which I call A naught, no subscript 0, meaning it's like the first term, over 1 minus your rate. Let's plug this in. What's our first term? It's 2 to the negative first, so that's going to be 1/2. And what's our rate? Well, our rate, we're multiplying by 1/2 each time to get each next term. Our rate's 1/2. And so I end up with 1/2 over 1/2. That's just 1. So 1 is my answer. Let's kind of work with a few more geometric series to get ourselves familiar with this kind of question. Take this and I'll move it up here. Okay, so let's say I had a series like 2/3 plus 1/3 plus 1/6 plus 1/16, or I mean 1/12, and it's going on and on forever, and I want the sum. Let's identify the two things we need to identify, which are our first term, which is 2/3, and what our rate is. Our rate, what number are we multiplying by each time to get the next term? In this case, it's 1/2. That's our rate. So the sum is going to be 2/3 over 1 minus 1/2, which is 2/3 over 1/2, which is 4/3. Let's do one more example. let's say we have 1 plus 2/3 plus 4/9 plus 8/27 and so on. So what's the sum? Let's identify the two things we need. What's our first term? Our first term is 1. And what's our rate? Our rate, this number we're multiplying by in each term, is 2/3. So now we can solve this question. So on the top we have 1, and on the bottom we have 1 minus 2/3. And so that's going to be 1 over 1/3, which is 3. That's our answer. And so now you guys know how to get the sum of any infinite geometric series. Alright, 58. The area of a 30, 60, 90 triangle with a hypotenuse length of 16 is k√3. What is k? Okay, so what's a 30, 60, 90 triangle? Well, like it says, those are the measures of the angles in the triangle. So it looks something like this. Oh. Like that. Oh, that could be drawn better. Come on. That's about as good as it's going to get. So, here, we have a right angle. That's our 90-degree angle. We have our 60-degree angle and our 30-degree angle. So an important thing to know about a 30, 60, 90 right triangle is that the sides are in a certain proportion. So if this side length is x, the side across from the 30-degree angle, then this leg is a length of x times the square root of 3. There's a little delay on my pen. Fix that. Okay, that's better. So, the leg across from the 30-degree angle, the shortest leg, is x. If it's x, then the length across from the 60-degree angle, the other leg, is a length of x times the square root of 3. The hypotenuse, then, has a length of 2 times x. So the ratio is always 1 to root 3 to 2. Okay? And we can use this to help us solve for the area. So, we're told, let me move this to here. So we're told we have a 30, 60, 90 triangle with a hypotenuse length of 16. And I want to find the area. So let's think. If the hypotenuse is 16, what is the shortest leg? It's 8. What's the longest leg? It's 8 root 3. Right? And now let's get the area of this triangle. You guys know how to solve for area. That's base times height over 2. Our base is 8. Our height is 8 root 3. We'll divide by 2. So the area of this triangle is 32 times the square root of 3. The question said that the area, if it's equal to k times root 3, then k is what? So k has to be 32. And so that's our answer. So make sure you know your 30, 60, 90 proportions. So that's the whole third column done. Now we just have the fourth column. So if you're new to number sense, you're probably not going to reach the fourth column on your first few tests. You have to be very fast to get to the fourth column. But I think it's good to show anyways. So here is the fourth column. Alright, so if 59, okay, so we have 59. So if x squared plus y squared is equal to 89, and x is greater than y, and x and y are both positive integers, then y is equal to, so I just got to think of my squares. Okay, can I use 9 squared? No. What about 8 squared? 8 squared is 64 plus 5 squared. That would work. And because x is greater, x has to be 8, and 5 has to be y. So y has to be 5. That's our answer. It's a pretty easy question. 60, another estimation. Let's look at what we got. We got 14 times 42 times 70 times 98. So let's get creative here. What can I do? Let's round a bit. Let's round this number here to 100. I'm rounding that to 100. I might as well round another number down. Kind of keep the estimation from going too far off the rails. So I'm going to move that 42 to a 40. Now I've got 14 times 40 times 70 times 100. And I can multiply, I'm going to multiply these two and these two. That's going to get me 980 times 40,000. I mean 4,000, my bad. So, I just multiply these two. I'm going to just pretend I'm doing 98 times 4. I think I'm pulling out those 4 zeros, which means I'm pulling out 4 factors of 10. So I'll put in those 4 zeros at the end. So 98 times 4, that's just going to be 392. Now I got back my 4 zeros. 1, 2, 3, 4. That's my answer. 3,920,000. And my range for that question was 3,831,996 to 4,235,364. So we were pretty close in the middle. Alright, let's do 61. Let's find all the find the sum of all the positive integers x such that 3x minus 6 is less than 9. So let's solve this equation. I'll add 6 to both sides. These cancel out. 3x is less than 15. Now I'll divide by 3 on both sides. And these cancel out. So I have x is less than 5. And I want to get the sum of all the positive integers such that it satisfies this condition. So I can't do negative numbers. I can't do 0 because 0 is not positive. Right? Not that it would matter if I added 0, but the only x values I can use are 1, 2, 3, and 4. I could use 5 if it said greater than or equal to, but it doesn't say that, so I can't use 5. So 1 plus 2 plus 3 plus 4, that's 10. So 10 is our answer. Number 32, if this 2 by 2 matrix equals 7, what's x? So when it says this matrix, which a matrix is just like these vertical lines and then like these numbers in specific rows and columns here. If it's saying it's equal to a number, it's talking about its determinant. How do you find the determinant of a 2 by 2 matrix? What does it mean? Well, the definition of determinant is beyond what we need to do in number sense. But the formula for it is what we do need to know. The formula, if you have a 2 by 2 matrix, A, B, C, D, the determinant is equal to A times D minus B times C. And so this equation is therefore saying that for this 2 by 2 matrix, A times D, so this kind of diagonal going this way, so the 2x, minus the diagonal going this way, 15, so that's 3 times 5, that's equal to 7. So we're just solving this little algebra equation. So 2x equals 22, x equals 11. 11 is our answer. See, now you know how to find the determinant of a 2 by 2 matrix. You can use it to work backwards, solve for one of the elements, and yep. Okay, 63. The inverse cosine. Inverse cosine of the sine of pi over 6 is equal to what? So the sine of pi over 6, okay. So you gotta be familiar with something we call the unit circle. So the unit circle. I mean, you could build a triangle, that's another way, but I like using the unit circle. Okay. So what the unit circle represents, it's like a circle with radius 1 centered at the origin. And here we got 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then a full turn 360 back to our starting point. And now, gotta know what it means for something like what does sine and cosine mean? What does that mean? Let's say I were to go here to, let's say, well, you know, let's go to 30 degrees. It kind of makes a triangle. The hypotenuse of 1. The hypotenuse is always 1. Well, the sine is the vertical component of whatever angle you're at. So we're at 30 degrees. So this is sine of 30. Sine of 30 represents that height of that triangle. Cosine theta represents the leg of that triangle, this horizontal component. So in this case, cosine 30. And there's specific values you gotta know. So the best way to memorize it, or the best way to learn it is to memorize it. So you could Google unit circle, go to images, and you'll see a graph like this, right? And you just want to study this. Like spend like 3 hours, 2 hours studying this image until you've gotten everything down. Now, this angle right here is 30 degrees. Even without memorizing the unit circle, you guys should be able to know what this height is. Because this is a 30, 60, 90 triangle. It is. So the height should just be half the hypotenuse. 1/2. Then, the leg, it has to be square root of 3 over 2. Let's see what the question wants. It wants the sine of pi over 6. That's 1/2. So now the question has turned into inverse cosine of 1/2. And so what we're saying is, what angle would give us cosine of 1/2? It's one that would look something like this. Specifically, turns out to be 60 degrees. And so the answer here is 60. 60 degrees is the answer for 36. Now, this is probably the most rushed explanation I gave, honestly. I feel it's way better to go and study unit circles and stuff like this on your own if you're not already familiar. Yeah. So I'd suggest looking at some other videos. Maybe one day in the future I'll go more in depth, make a video entirely dedicated to the unit circle. We've got to move on right now. Alright, so I'm going to do a jump cut right here. Okay, so we're back. And let's continue on with number... Oh, didn't I already put this? 60 degrees. That's the answer there. I think earlier what I said, I think I misspoke. I said, because we evaluated sine of pi over 6 was going to be 1/2. When I said like we were looking for, I think I said we were looking for what angle would give us a cosine of 1/2. That's not true. What I mean is, what angle when we take the cosine of it gives us 1/2. So that's a little correction I wanted to make. Okay, so 64. Question 64 says the volume of a right cylinder. Okay, the volume of a right circular cylinder is 32 pi centimeters cubed. So the volume is 32 pi. Find the height if the radius is twice the height. Okay, so then maybe that's not the most accurate drawing. So, not that the drawing matters, not like you're gonna, make a mental image of it, but I think it looks nice to have a drawing. So So the radius is twice the height. Actually, it'd be more wide than that. Be like this. So we have the height. Okay, well the radius is equal to double the height. So let's substitute the 2r for r in the expression for the volume. Right, so this length here would be 2h. And this length would be h. Okay, so what is the expression for the volume of a cylinder? So the volume of a cylinder is equal to pi r squared. Well, that does not look like an r. Pi r squared times height. Pi r squared being the area of the base, which is a circle, times height. So area of the base times height. And we know r squared is 2h, so let's substitute that in to our expression. So instead of r squared, we have 2h squared. Let's evaluate this. So volume is equal to pi times 4h squared times h. We simplify this a bit more, we get 4 times pi times h cubed is our volume. And we know what our volume is. It's 32 pi. So we can set this equal to 32 pi. We can cancel the pi's out. Then we can divide both sides by 4. These 4's cancel out. And we're left with h cubed equals 8. So h is 2. So 2 is the height of our cylinder. So, you know, in this test, like what you want to be thinking is, okay, pi r squared times h, and the radius is twice the height, so pi times 2h squared times h, so that's pi times 4h squared times h, so that's pi times 4h cubed, so they equal to 32, the pi's cancel out, divide by 4, I get 8 equals h cubed, 2 is h. Something along those lines. Okay, so 65 is another trigonometry question. So we want to find the inverse sine of cosine of pi over 3. I think I will make a unit circle video eventually. So this is going to be a little bit of a rushed explanation. So that is not a circle. Closer. That's as good as it's going to get, guys. Sorry about that. Okay, so our angle is pi over 3, which is 60 degrees. I don't think I said it earlier. Pi radians is the same as 180 degrees. So if I have pi over 3 degrees, I have 180 over 3 degrees, or 60 degrees. So whenever you see pi in something involving trigonometry and angles, think 180 degrees. Okay, so we have a 60-degree angle we're working with. So something like that. Kind of make this height. This height right here would be our sine component, and this base right here would be the cosine component. And of course that's 1. Okay, so we have our 60-degree angle, and we want to find the inverse sine of cosine of pi over 3. So what's cosine of pi over 3? Well, here, this is a 30, 60, 90 triangle. So if our hypotenuse is 1, what's the angle across from this 30-degree angle? It's going to be 1/2. So cosine, which is that horizontal component, is 1/2. So now we're doing the inverse sine of 1/2. And so what that's saying is, what angle, when we take the sine of it, gives us 1/2? So it would be an angle that looks something like this, where we have 1 for our hypotenuse and our sine is 1/2. That means this leg of the triangle is half the hypotenuse. So this would be like the 30-degree angle in a 30, 60, 90. And so our answer is 30 degrees. So that's number 65. 30 degrees is our answer. Okay, number 66. So I have this infinitely repeating decimal, so 0.020202 forever. Base 5. I've got an infinitely repeating number in base 5, and I want to change it to some number in base 10. As a fraction. So I'll note that right here. Fraction. So typically when we have a question like this, in base 10, like if I saw 020202 repeating, and I think I might have said this in the last video, but typically we see two numbers constantly repeating, we just put, our answer would be just those two numbers, so 02, or just, 2 over 99. That's if our repeating number is in base 10. In this case, we have it in base 5, so what do we do? Well, we actually do something very similar. So because we're dealing with base 5 in this case, instead of putting the number, these two repeating numbers, so 2 in this case, instead of putting it over 99, in this case, we're going to put it over 44. And so why do we do it over 44? I mean, there's probably like a long explanation, but the way I like thinking about it is if I had the same case in base 10, well, the denominator is going to be like 1 less than the base, so 9, but 2 9s because we're dealing with two repeating numbers. And I like to think of it like the same way here. I'm dealing with base 5. I'm going to do 1 minus. It's going to be 4. I'm dealing with two repeating numbers, so 44. If I were dealing with three repeating numbers, like if I had 0.123, 123 repeating in base 5, I'd say the answer is 123 over 444. 4 being the highest number that you can have, in the decimal place, or in a place value, I guess. But we're not done. We can't just say the answer is 2 over 44. We got to make sure that we simplify this fraction. Now in this case, it does just simplify. Well, it doesn't simplify actually nice at all. Instead, we have to divide 44 base 2 by 2. Now why can't we just divide it by 2 and say, oh, 22, 1 over 22? That would get you the wrong answer, because we're not dealing with base 10, we're dealing with base 5. Oh, why did I put 2 here? My bad. We're dealing with base 5, So how can we divide a number in base 5? So the way I'll divide here, instead of like doing long division like this, what we're going to do is we're going to change 44 base 5 into base 10. So let's do that trick from before in the last video. We're going to do 4 times 5 plus 4. That's going to get us 24. So 44 base 5 is 24 base 10. And then 2 is just going to stay the same. It's going to be 2. So I change the numerator and denominator of our fraction in base 5 to base 10. Okay, so now, because we're in base 10, I can just divide. So I get 1/12. And that's my answer. That's my fraction in base 10. Let's do another example. So 1/12 is our answer. Okay, so let's say I'm still changing this to a base 10 fraction. But now my numbers are 23, 23, 23. So let's do the steps in the process again. I see we're dealing with 2 repeating numbers, so it's going to be over 44. Actually, let's change the base. Let's change it to base 7. Base 7. Okay, so what's my denominator? 1 less than 7 is 6. How many repeating digits am I dealing with? Dealing with 2. So it's going to be over 2 6s, 66. My top being those 2 repeating digits, so 23. But this fraction's in base 7. I want it in base 10. So let me change the numerator and denominator to base 10. Let's start with the denominator. Let's do our trick. 6 times 7 plus 6. 6 times 7 is 42 plus 6 is 48. So 48 would be my denominator here. Let's do the same thing with the numerator. 23 base 7, so here 2 times 7 plus 3. 2 times 7 is 14 plus 3 is 17. So 17 over 48 is my answer. Okay. So now let's try working with base 5 again. This question is going to be a little different. So let's say I'm dealing with (24, 24, 24). Or how about, actually, better one, 34, 34, 34. Okay, so if we do our trick, actually no, one extra thing I want to change. Let's keep it as a base 5 fraction. You'll see why I'm doing that. Okay, so let's do our trick. So how many digits are repeating in this case? Still 2. So 1 less than 5 is 4. There's 2 numbers repeating, 44. And the top is going to be 34. Am I done? I'm not done. Or am I? You might think I can simplify to 17 over 22. But you'd be wrong because we're still in base 5. We can only divide right now in base 10. So we need to check if we can simplify first by changing this fraction to base 10. And if we do that, I get 24 here on the bottom. And on the top, I get 19. We see that it doesn't simplify. So our answer remains as is, 34 over 44. And that might look like a cursed fraction, right? Like obviously you'd think this should simplify, but it doesn't because we're not dealing with base 10. We're not dealing with the normal rules we're used to. We gotta see if we convert it to base 10, this fraction, if it simplifies. And if it doesn't, well then it doesn't. And even though it looks kind of cursed, that is the answer. So 34 over 44 without reducing. And sometimes you'll see questions like that, where you think you have to reduce, the answer looks like you should reduce, but you don't have to. So 67. Okay, so if 14 to the 4th divided by 4 is equal to 2 to the x times 7 to the y, then what's x plus y? Well, 14 is made up of factors of 2 and 7. This is just 2 times 7 to the power of 4. And if we're dividing by 4, it's like we're dividing by 2 squared. And that's equal to 2x times 7 to the y. Now I can simplify this part. I could distribute that 4. This is equal to 2 to the 7th times, well, my bad, 2 to the 4th times 7 to the 4th divided by 2 squared, and that's equal still to this expression here on the right hand side. Okay. Here I can cancel out some of the 2's from the 2 to the 4th with the dividing by 2 squared expression here. So I'll get 2 squared times 7 to the 4th is equal to 2 to the x times 7 to the y. So, therefore, 2 and 4 have to be x and y, the sum of which being 6. So we wanted to break up 14 into its factors, 2 and 7, distribute that power of 4 to them, do some canceling out with the 2 squared, which comes from the 4, and then see what we've got left. So that one's not too bad. It's a little bit of algebra. Number 68. So this expression has a remainder of, okay, so that may look really bad. Those of you who've already done Algebra 1 might be thinking, do I have to do synthetic division here? Or long division? You don't. There's a trick you can use to get the remainder here. the way you can get the remainder of this expression when divided by x plus 1 is you set this number which you're dividing by, set it equal to 0 and solve for x. X would be -1. What you're going to then do is take this value of x and substitute it into this expression. So I would get 2 times -1 cubed plus -1 squared plus 3 times -1 plus 4. Now I evaluate this expression, so this is going to be -2. Wait, can you guys see? Or am I blocking the question? I might be blocking the question. Hold up. There, we're dealing with 68. I can't exactly see where my webcam is right now. I hope I didn't block that for you guys. That would be bad. So here I get -2 plus 1 minus 3 plus 4. So -1, -4, 0. This comes out to 0. And this number that I get from substituting this number right here into the expression is my remainder. Really, this is my remainder. So no long division, no synthetic division, none of that's needed. Just set that number which you're dividing by, right? Set it equal to 0, solve for x, and substitute it in to the number in which you're dividing. And that will give you your remainder. So let's do a practice question. Let me make up a expression here. Let's say 4x to the 4th plus 2x squared minus 7x plus 7. And we're going to be dividing this by x plus 2. Let's solve for x. When we set this equal to 0, this would be -2. So when I substitute in -2, I'll get 64 here, I'll get an 8 here, I'll get -14 here, and +7. So I combine everything and I'll get 65 as my remainder. Okay, so now you know how to find the remainder when you're dividing two polynomials. Okay, so number 69. This one's pretty easy. We just have this expression for f of x, and I want to find f of -1. So I'm just going to plug in what I get when I... Okay, well first, let's break it down. Let's do f of -1. So I'm going to represent this step in orange. So I'm going to do 4 times -1 squared minus 1, and that's equal to 3. Okay? And now, because f of -1 is 3, I can substitute 3 in here. Because it's that. And now I'll do 4 times 3 squared minus 1. And that's 35. So this one's pretty just basic algebra. So plug in -1, and then plug in what you get back into the expression. Alright, so if I had f of 2, what I would do is I plug in 2 and I get 15, right? So I get 15 here, then I plug it in, so I'm doing f of 15, and from there I get 4 times 225, which is 900, minus 1, that would get me 899. Okay, number 70, estimation. So what we can do here, okay, well, we're dealing with this number. If you're really math savvy, you might know that this number here is the golden ratio. Golden ratio. That's going to be 6.1828 something, pretty sure. Anyways, so because that's the golden ratio, okay, well, what can we do here? So yeah, it's about like 6 points, like 1.62 almost. So one thing we could do, I mean, we could round it down to 1.6 and then account for it later on. I know that 16 cubed. Okay, so here's like what I'm thinking. This one's a tough one. I'm thinking that this is basically 1.6 to the 10. But then we'll add some amount later, right? And so it's like 1.6 cubed times another 6. The reason I'm saying that is because I know what 1.6 cubed is, because it's like 16 cubed. It would be like about 41? No, 4.1. Because 16 cubed is this number right here. It's 4,096. So 1.6 would be 4.196, which is about 4.1. Round up a little there. So it's like 4.1 cubed times 1.6, which this is like, if I round down, it's like 4 cubed times 1.6, so that's 64 times 1.6, which gets me about, okay, so that'd be like, I think I'm like estimating a bit. I would say that's about 100, like 102, right? But I gotta add a bit more because I rounded down a lot. Because I simplified this, instead of being like 1.61828 to the 10th, I said it was like 1.6 to the 10th. And even though that's like only a little bit of rounding, because we're raising it to the power of 10, that's like a lot. And so I'd probably add like maybe 20? Okay, well, let's see what the range is. Basically, okay. The range for this question is 717 to 729. It's a pretty narrow range, so you gotta be real specific. 122 does pass, but it's kind of like a nasty question, honestly. There might be a better way, but I'm not really sure. So I don't know about the way I did it. If you guys know a better way, let me know, but I don't really like that question. So 71. Want to change 3 over 25. This is in base 10. To a base 5 decimal. This is kind of like 66, but instead of going from decimal to fraction, I'm going fraction to decimal. So how can I do that? Well, the way I'm going to do this, I want you guys to think about it as if I'm going to keep dividing by a fifth. You'll see what I mean. If I divide 3 over 25 by a fifth, I get 3 over 5. What is my whole number here? There is no whole number, right? So I'm going to put, at my decimal point, I'm going to put 0. Then I'm going to keep dividing by a fifth. So I divide by a fifth again, and I get 3. Do I have a whole number? I do. And there's no remaining fraction part. So I'm going to put down that 3. We're done. The answer is 0.03. Let me give you guys another example. Let's say I had 14 over 25 base 10, and I wanted to a base 5 decimal. So I'm going to do 14 over 25. I'm going to divide by 1 over 5, and that's going to get me 14 over 5, which is 2 4/5. Do I have a whole number part? I do. So after the decimal place, I'm going to write it down. I'm going to write down 2. Okay, so now I'm going to take that 2 away. I'm going to take this 4/5. I'm going to divide it by a fifth. So we keep dividing by a fifth. And I get 4. There's no fraction part, so that tells me I'm done. So I'll write down the 4, and that's my answer. So now you guys hopefully know how to go from fraction to decimal form. We're just going to divide by 1 over the base each time. And write down what we get as the whole number part of our quotient. We're going to keep dividing and dividing, basically. And once we write down that whole number part, subtract it, keep dividing, until we end up with no fraction parts. Okay, 72. So find x if x is in between 0 and 4 inclusive, if 16 plus x, these are 3 lines here, meaning 16 plus x has a remainder of 4 mod 5. Okay, so let's clarify some terms right here. So this part right here, these 3 parallel lines, what this means is basically has a remainder of, that's what it means. So if 16 plus x has a remainder of 4, and what mod basically means is when divided by, that's basically what mod means. So we put it all together, we're saying x is between 0 and 4. Okay, so for x, which is in between 0 and 4 inclusive, if 16 plus x has a remainder of 4 when divided by 5, right? So I'm solving for x, I'm finding x. And so, I gotta think, okay, what number x can I add to 16, that is between 0 and 4, that gives me a remainder of 4 when I divide this number by 5. Well, 16 already has a remainder of 1 when I divide it by 5. So to get it to a remainder of 4, I'll need to add 3, right? So 3 is my answer, right? 16 mod, I could say 16 mod 5 is already 1. So 16 plus x, for this to be 4 mod 5, x has to be, oh, I wrote this a little wrong. My bad. So 16's already like that. So 16's already 1 mod 5. Already has a remainder of 1 when divided by 5. So for 16 plus x to have a remainder of 4 when divided by 5, x would have to be 3. 3 more. So 1 plus 3 is 4. Okay. 73 is some calculus here. So f prime of x is equal to 3. Then f of 2 and f of 2 equals 5. And find f of 1. Okay, so let's get some of this notation cleared up. What is x prime, or f prime of x? This is the derivative of f of x. So what's the derivative of a function? Might be a bit much to go over, some calculus stuff. But basically, what you can think of it as, and I'll give you like a real rough explanation. So if this were my function f of x, then my derivative, so f prime of x, I would get it by doing something called the power rule when I have this polynomial. So the power rule goes that I'll take this exponent and I'll multiply it in front of this coefficient, and I'm going to do 1 less than the exponent. So I'm going to get 6x to the first. Let's practice a little bit. Show you what I mean. Let's say I had 4x squared plus 5x, and I want to find f prime of x. So let's drop that exponent down for each of these terms. So this would turn to an 8, because 4 times 2. This is, 5x, just 5x to the first. 5 times 1 is still 5. And then I subtract 1 from each of the terms. Powers, right? And so the x to the second turns into an x to the first, or just an x. The x to the first turns into an x to the 0, which is just 1. So the derivative would be of, the derivative of 4x squared plus 5x to the first is 8x plus 5. Okay? That's basically the power rule. And what we're doing here is we want to kind of build a function from our derivative. And here's another property I want to show you guys. So let's say this function had a constant term here, this original function. Well, you can pretend there's an x to the 0 here. I multiply by 0, this function, goes away. Not function, this part of the polynomial goes away, right? And when I try reversing the power rule, so it would be like, I know that the next exponent above 1 is 2, so I'd divide by 2 to get 4. And then I'd raise the exponent 1. I'd find what that leading coefficient is. I'm back to where I started. Same thing here. This is basically an x to the 0. I know the next power of x is 1, so I'm going to divide the 5 by the 1, which is still 5. and then I'm going to raise the exponent on the x to the 0 term. So that's going to be x to the first. But because this constant term doesn't show up in the derivative, I would have no way of knowing if this were 7 or 71 or 17. I would have no information about what that constant term is from the derivative. It doesn't give me any information. So, when finding a function from its derivative, so I'll write this in blue. Again, I know the next power would be 2, so I divide this by 2. So this would be 4x squared. And I know the next power is 1, so I'm going to divide this by 1. So that's going to be plus 5x to the first, or just 5x. Because I'd have no way of knowing if there even was a constant term or not, we always put plus c when we do this reverse derivative, this antiderivative. So how can I find out what the original function is? Well, let's look at this question. Back to our original question. Okay, so if f prime of x is 3, then what's f of x? Well, this is basically 3x to the 0. I know the next term, or next power of x here is 1. I'll divide the 3 by the 1. I get 3 times x to the first, which is just going to be 3x. But plus c, right? Because I don't know what that constant term would be. And so, how do I find my constant term? I use this piece of information the question gives me, that f of 2 is 5. That's really valuable because now I know that if I do f of 5, or no, f of 2, it's going to be 3 times 2 plus some constant c. I know that this is 5. I can solve for c. In this case, c would be -1. And now I can finally build my function. F of x is equal to 3x minus 1. That's my function. And now I can plug in f of 1. I plug in 1, I get 2. So that's a lot of calculus stuff. Let me show you guys how you can do this question fast. Like the basic trick, like what it comes down to. Apart from all these definitions of derivatives and antiderivatives. If you ever see f prime of x is equal to some number a and f of some number b equals some number c, to build the function, the original function, f of x, it's going to be a times x plus, what you do here, this constant term would be c minus a times b. C minus a times b. And so, let's try this out. So, we go back to our original expression, original question, I mean. This is 3, and this is 5 for C, and 2 for B. Well, then my function is therefore 3x plus 5 minus, well, again, this is 2 times 3, so 5 minus 6. 3x minus 1. We got back to our original function, just like that. Now, I think questions like this take a lot of practice to get used to. I don't really want to talk a lot about these last column questions because, again, I'm mainly trying to help people who are new to number sense or who are trying to get to the third column. This stuff at the very end of the fourth column is for those who probably don't even need to see this video, to be honest. But I think it's good to touch on these topics to kind of get used to them, or get introduced to them is a better word. Okay, so I'm not going to do some more examples of 73. Okay, 74. Y is equal to log base 3 of x, has a vertical asymptote at x equals some value, right? So what does it mean for this function to have a vertical asymptote at a point? Well, it means that when you plug in, what our answer would be, that value that gives you that vertical asymptote, means when you plug it in, you're going to get something that's indeterminate. And that value is going to be 0, and here's why. Let's think about what log means again. What this is saying is 3 to what power gives me x? And why 0 works is because I'm saying 3 to what power gives me 0. There is no such number. The closest you could get to is negative infinity, right? It'd be like if you flipped it, so you made it the exponent negative, and you kept getting like the square root or something like that. Or kept squaring it, I guess, raising it to higher and higher powers. So it gets close to 0. But 0 is going to be the answer here. And I guess the quick way of doing this is if you have some function log of base a of x minus h, right? The asymptote is going to be h. In this case, this is like x minus 0, so 0. That's the quick way. Okay, 75 limits. Okay, we're just going to plug in 3 here. If you plugged in 3 and you got something like that give you like 0 over 0, that means the limit's like an indeterminate form, so you gotta do like fractions or not fractions, but factoring, canceling out. But we're just gonna plug in 3 because it's gonna end up all right. It's gonna be 8 over 10, so 4/5. Yep. Okay. So 76. We have f of x is equal to cosine x. And I want to find f prime prime of 60 degrees. Okay, so f prime prime, that means again the second derivative. And yeah, this is very, very calculus heavy. So for those of you who already know calculus, if I had sine of x, this is like y. Well, then y prime would give me cosine of x, and then y prime prime, so y double prime gives me negative sine of x, and y triple prime gets me negative cosine of x, and then y prime 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 gets me sine of x. And so it basically all loops around, like we go back to where we started. And so in this case, we take the second derivative of cosine, we're going to get negative cosine. So the answer is just going to be negative cosine of 60 degrees, which would be negative 1/2. Again, cosine of 60, just memorize unit circle, it's 1/2. So negative that, so negative 1/2 is our answer. Okay, 77. The integral, okay, here's a trick I don't see a lot of people doing. They'll actually evaluate this integral like by hand. But in this case, I think it's better to visualize it. Let's think about what's going on. So we have this line. This is y equals 3 plus x. So it's like from here to here, 0 to 3. And I want to get the area under this curve, right? That's what it means to get the integral from 0 to 3. Get the area from 0 to 3 under the curve of 3 plus x. And we can see that this area is just a trapezoid. It's just a trapezoid, with one base being equal to 3 and the other being equal to 6. And this width is 3. So it's just the area of a trapezoid. So we're going to do base 1 plus base 2 times height over 2. That is just going to be 27 over 2. That's our answer. Or you could integrate it, but I think that's a little slower, getting the antiderivative, plugging it in. I like visualizing if I can for integrals. Okay, 78 for Mont's little theorem. Right? Wrong. Here's why. So for Mont's little theorem, it tells us that n to the p minus 1 divided by p, it's always going to have a remainder of 1 mod p. But the thing is, we can't tell, in this case, like we could tell if it were 7 to the 10th divided by 11, but we can't tell if it's 7 to the 9th. So what can we do? Let's use modular arithmetic. So 7 to the 9th. That is the same as 7 cubed. And so that's 373 cubed. Let's divide 373 by 11. 373, well, mod 11. Let's get what that remainder is. It's going to be 2. So using modular arithmetic, I could say that this remainder, whatever this is, mod 11, is the same as 2 cubed mod 11, which is 8. And so 8 is my answer for 78. So we had to use modular arithmetic to get what we wanted. So we kind of had to be a little creative with this question. So yeah, modular arithmetic, very powerful tool. Okay, 79, we're almost done. Okay, so 1 gallon, okay. So gallon to quarts to pints to cups to ounces. Right? Now, there's 2 extra ones you gotta know about, so grab these. These are bigger than a gallon. That's a bushel and a peck. So first let me show you, starting with gallons. If I had 1 gallon, I have 4 quarts, and I have 8 pints, 16 cups, 128 ounces in a gallon. So I have to multiply by 4 here, have to multiply by 2 here, have to multiply by 2 here, I have to multiply by 8 here for each successive step. Now, just looking in this area here, from bushel to peck to gallons, if I had 1 bushel, I would have 4 pecks, which would give me 8 gallons. So to get here, I have to multiply by 4, and to get here, I have to multiply by 2. So you could just remember this like 4, 2, 4, 2, 2, 8. You have these two like 42s and then a 28. Well, not really a 42, but like, you know, just kind of remember it as 42. It's like multiply by 4, then multiply by 2. You know what I mean. Sometimes they'll ask about bushels and pecks in these questions. And so anyways, so I'm converting all of these into cups. Well, actually what I'll do first, I'm going to convert gallons to quarts. So 1 gallon is 4 quarts. I'm going to add that to the 2 quarts here to get 6 quarts. So 1 gallon plus 2 quarts is 6 quarts. Then I'm going to convert quarts to pints. So I'd have to multiply by 2 and get 12 pints. Add the 3 pints, I get 15 pints. Times 8 to get it to, or no, times 2 to get it to cups. And I got 30 cups. So that's my answer. This one's just like a conversion question, dealing with conversions. Alright, so now we have the last question. Finally done with this test. So number 80. 1428.57 times 69. So what's that going to be equal to? Well, the trick for this question comes from recognizing that this number right here is basically, it resembles the digits of 1/7. 1/7 being 0.142857 repeating. This little bar at the top represents that it's going to be those same 6 numbers repeating over and over infinitely. And so really this number is like, instead of 1/7, it's like 10,000 over 7. So what I can do is I could treat this question as 10,000 over 7 times, I'm around the 69 to a 70. Again, I can round because this is an estimation. And so the 7 and the 70 cancel out, leaves me a 10. And so I get about 100,000 as my answer. So this one's not too bad. But you have to know, you know, your sevens, right? And that's pretty close because the answer range is 93,643 to 103,499. So we're right there in the middle, kind of. Alright, so that is the whole second page of the UIL A number sense test from 2018. If you have any questions about this video or the stuff I've gone over, be sure to leave them in the comments below. If you have a better trick yourself, please let me know about it so I can share it on this channel. I'm hoping to upload at least 3 times a week for the rest of the summer. Yeah. Alright, so I'll see you guys later.